Modern AI is absolutely incredible at finding patterns, but there's a much deeper kind of intelligence, one that's been really hard for machines to grasp, understanding cause and effect. Today, we're going to dive into some fascinating new research that teaches an AI not just to see the world, but to actually think like a scientist.
Okay, so let's start with a classic example, one you've probably heard before. There's a known correlation between ice cream sales and shark attacks. But obviously, buying a cone doesn't summon a shark. There's a hidden factor, what scientists call a confounder, and in this case, it's hot weather. Right? Hot weather makes you want to buy ice cream, and it makes you want to go for a swim. More swimmers, sadly, means more shark encounters. For you and me, that's just common sense. But for a machine, telling that kind of correlation apart from real causation is one of the biggest hurdles in all of AI.
So that brings us to the big question, the million-dollar question, really, that researchers are trying to answer. Can we actually build a machine that learns to tell the difference all by itself?
And the breakthrough idea here is a total game changer. Instead of trying to painstakingly code every single complex rule of causal logic into an AI, what if you could teach it how to discover those rules for itself? What if you could teach it not just what to know, but how to learn?
The magic behind all this is a really cool concept called meta-reinforcement learning. Now, what is that? Well, think of it this way. Instead of training an AI to be great at just one specific thing, you throw thousands and thousands of different kinds of puzzles at it. Over time, it doesn't just get good at solving those specific puzzles, it actually starts to learn the process of problem solving itself. It's literally learning how to learn.
So how does this learning to learn thing actually work? Well, it's all about this two-loop system. First, there's the slow outer loop. This is where the AI grinds through thousands of different causal puzzles, slowly but surely building up an intuition for how cause and effect works. This long training process shapes its internal network into something new, a super-fast inner loop. This inner loop is basically a ready-to-go learning machine, so when you give it a totally new puzzle it's never seen before, bam, it can often figure it out almost instantly.
All right, so to really put this new AI to the test, the researchers didn't just give it a quiz. Oh no, they created the Gauntlet, a series of 3 increasingly difficult challenges designed to push this AI to its absolute limits.
First up, we have test number 1, the detective. And the name says it all, really. The AI's role here is to be like a detective at a crime scene. It's not allowed to touch a thing. It can only watch and try to piece together what really happened.
So this setup is what's called an observational setting. The AI just gets a fire hose of data from a system, and from that data alone, it has to untangle this whole web of connections. Now, sometimes if the problem is structured just right, you can figure out cause and effect just by watching. The question was, could this AI learn how to do that kind of advanced reasoning on its own?
And the results? Well, they were pretty incredible. The Causal AI, our new agent, just blew the other model out of the water. I mean, it dramatically outperformed a standard AI that could only see correlations. It had figured out how to reason about cause and effect. So, test 1, passed with flying colors.
But here's the thing. Just watching from the sidelines isn't always enough to solve the really tricky puzzles. So for test number 2, the researchers basically took the handcuffs off. Now the AI could act like a real scientist in a lab, running its own experiments to see what would happen.
The real challenge here, the thing that makes this test so much harder, is dealing with those unobserved confounders. Remember our hot weather example? Well, imagine trying to figure out if exercise makes people healthier, but you have no idea how old they are. Age is a huge confounder, right? It affects both how much people exercise and their baseline health. If you can't see it in the data, you're just stuck. The only way to solve a problem like that is to intervene, to run an experiment. And that is exactly what the AI learned to do. The moment it was given the power to intervene, to actually experiment with the system, its performance just skyrocketed. And you can see it right here. The improvement was the biggest in exactly those cases with hidden confounders, the very puzzles that were impossible to solve just by watching. Test 2. Passed. But here's what's really cool. The AI didn't just start flipping switches at random. No, it learned to be a good scientist. It learned how to choose the most informative experiments, the ones that would give it the biggest bang for its buck, the most useful data to solve the puzzle. An AI that actively chose its experiments consistently and significantly beat an AI that was just intervening randomly. Okay, so for the final test, the big one, the most difficult one, the AI had to do something that sounds like science fiction. It had to become a time traveler. It was asked to reason about things that never even happened. This is the world of counterfactuals.
So what exactly is a counterfactual? It's basically a what-if question about something that already happened. Like, you could look at a specific person's actual medical history and ask, okay, but what would her heart health look like if she had exercised more? This isn't about averages across a population. It's about predicting a specific alternate past for one individual.
Now, to pull this off, the AI has to do this really clever three-step mental trick. First, it looks at what actually happened to figure out all the unique hidden variables at play, things like that person's specific genetics. Then it has to mentally go back in time and change just one thing. And finally, it uses its knowledge of those hidden factors to run the simulation forward and predict the new alternate outcome.
And you know what? Incredibly, it worked. The AI that could think in counterfactuals did even better than the one that could only intervene. And it really shined in these tricky cases where, just looking at the averages, multiple choices seemed equally good. By understanding the unique, hidden details of a past event, it could make a smarter prediction. Test 3, pass. So, after running through this whole gauntlet, what's the verdict? What have we learned here? Well, this isn't just a small step forward. This really feels like a new kind of intelligence.
I mean, let's just recap for a second. This AI learned to figure out cause and effect just by watching. It learned how to solve for those tricky hidden variables by running its own experiments. It even learned to answer those mind-bending what-if questions about the past. And the whole time, the crucial part is it was learning how to be an efficient experimenter.
Okay, so why should you care about this? Why does any of this matter outside of some niche computer science lab? Because this, right here, could change everything we expect from our machines. What we're looking at is really the first step toward building an AI that's, well, genuinely curious. An AI that doesn't just sit there and find patterns in the data we feed it, but one that actively goes out, explores the world, makes its own hypotheses, and designs experiments to figure out how things really work.
And that leaves us with one last kind of mind-blowing thought. For all of human history, scientific discovery has been our thing, right? It's been a uniquely human job. But if an AI can learn to design its own experiments, what's it going to discover next?